Welcome to the front line of the clean energy revolution. In 2026, the pulse of our global transition away from fossil fuels isn't found in a distant oil field or a remote mine. It resonates within the sterile, high-precision halls of the modern battery factory. This is where the future of mobility and power storage is forged. Cut to a montage of extreme close-ups, shot with a macro lens. We see raw powders, black graphite, white salts, flowing into immense, shining steel mixers. The visuals are almost abstract but highly detailed, emphasizing the purity of the materials. Every single day, billions of decisions are made by sophisticated machines to turn raw chemistry into a compact, robust source of power. It is a symphony of automation and exact science, a masterpiece of modern engineering designed to meet unprecedented global demand. This is a dynamic shot of a thin silver foil moving at incredibly high speed under a coating nozzle. The precision is evident. Then, a quick cut to robotic arms moving with millisecond precision, placing components into a jig. The speed and synchronization are mesmerizing. From the initial, critical blending of active slurries in a vacuum environment to the final, essential electrochemical activation process, we operate in a world where every single micron counts. This is not casual manufacturing. This is a journey defined by extreme, controlled conditions. This is the key metrics: humidity less than 0.5%, tolerances plus or minus 5 microns. We are in an environment where humidity levels are kept near zero, drier than the world's most arid desert, and where mechanical tolerances are measured in the width of a single human hair. It is the only way to ensure the safety and longevity of the product. Today, we step inside this technological sanctuary. We will witness, stage by stage, the meticulous, three-part evolution of a lithium-ion cell, the vital, beating heart of our electrified future. This is how power is made. Stage 1. Electrode manufacturing. This is complex industrial machinery. A faint hum of machinery is audible, as you can see. Every battery's life begins in stage 1, the creation of the electrodes. This crucial phase establishes the internal active layers, the cathode and the anode, that are fundamentally responsible for storing and releasing the electrical energy that powers our world. Slurry mixing, the chemical cocktail first, cut to extreme close-ups inside enormous, sterile, stainless steel vacuum mixers. Various fine powders, grey, black, and white, are being poured into the vortex of a rotating mixer head. Slurry mixing is where the chemistry truly begins. We combine the core active materials, specifically chosen lithium metal oxides for the cathode, and highly refined graphite for the anode. These are not merely mixed, they are engineered into a perfect blend using high-speed, vacuum-sealed industrial mixers. We introduce critical additives, conductive agents, which ensure efficient electron flow, and specialized polymeric binders, which act as the glue to hold the structure together. This process creates a uniform, highly viscous liquid known as slurry, a precise, potent chemical cocktail where consistency is paramount. Coating and drying, laying the active layer. This is a wide shot of a massive, long industrial line. A continuous sheet of shimmering metal foil feeds into a machine, emerging coated with a precise, even layer of black slurry. Next is coating and drying, a monumental engineering task. The slurry is applied in microscopic, precise layers onto incredibly thin metal foils, aluminum for the cathode and copper for the anode. This is done with a level of uniformity that is key to performance. The coated foil moves into a long series of ovens. You can see the heat sensors are visible. The foils then traverse through extensive industrial convection ovens. Here, the solvents are evaporated, leaving behind a dry, solid, active material fixed to the foil. This drying process is notoriously time-consuming, often consuming nearly 48% of the total manufacturing time of a single cell, but its thoroughness is non-negotiable for safety. Calendaring, compression and density. A macro shot of the dried, slightly fluffy-looking electrode sheet feeding into a set of large, heavy, mirror-polished steel rollers. It emerges visibly flatter, denser, and smoother. Calendaring is where we apply immense physical pressure. The dried electrode sheets are passed through heavy, high-precision rollers. This compression step is vital. It densifies the material, optimizing contact between the active particles and significantly increasing the battery's final energy density and improving overall electrical conductivity. Slitting and notching. Precision shaping. This large mother roll is mounted on machine. Circular blades spin rapidly, slicing the wide sheet into several narrow, perfect strips. A subsequent machine performs rapid, stamping motions, cutting out small tabs on the side of the strip. Finally, we move to slitting and notching. The wide mother rolls are precisely sliced into narrow, manageable strips. These strips are then shaped to their specific cell format, with small, critical tabs carefully cut, or notched, into the material. These tabs will serve as the connection points for the positive and negative terminals, ensuring the seamless transfer of power in the finished product. Stage 2, cell assembly, the architecture of power with our electrodes prepared, we move into the heart of the factory, the assembly line. This is a high-speed, ultra-dry environment where the chemical components we created in Stage 1 are physically integrated into a functional energy storage device. In this stage, speed meets microscopic precision. Stacking or winding. Building the core high-speed robotic arm involves rapidly spinning a mandrel for cylindrical cells or stacking rectangular sheets with lightning-fast pick-and-place movements for pouch cells. The first step is stacking or winding. Depending on the final application, whether it's a cylindrical cell for a high-performance EV or a prismatic cell for grid storage, the cathode and anode are layered with a porous, micro-thin separator between them. This separator is the unsung hero. It prevents a short circuit while allowing lithium ions to pass through freely. A close-up of the jelly roll, cylindrical, or electrode stack, pouch prismatic, being held by a robotic gripper. In cylindrical formats, these layers are spun into a tight jelly roll. In pouch formats, they are stacked in alternating layers. This assembly is the engine of the battery, and any misalignment here, even by a fraction of a millimeter, could result in a rejected unit. Casing and tab welding. Structural integrity visual. The assembled stack is lowered into a gleaming metallic canister or a specialized laminate pouch. A laser, appearing as a bright point of violet light, zips across the top of the cell. Next, we move to casing and tab welding. The assembled core is inserted into its protective housing, a rugged metal canister or a flexible, high-strength pouch. Using advanced ultrasonic or laser welding technology, the electrode tabs we notched in Stage 1 are fused to the current collectors. These welds must be perfect. They are the bridges through which every amp of current will flow during the battery's life. Electrolyte filling, the ionic gateway. The cells move into a vacuum chamber. A needle descends into the small opening of the cell, injecting a clear, precise amount of liquid. Now, we introduce the lifeblood of the cell, electrolyte filling. This process occurs in a strictly controlled vacuum to ensure there are no air bubbles trapped within the layers. A precise volume of liquid electrolyte, a complex mixture of lithium salts and organic solvents, is injected. This liquid permeates the porous electrodes and separator, creating the medium that allows ions to travel between the anode and cathode. Sealing, locking the system. A mechanical press crimps the lid onto a cylindrical cell, or a heated bar clamps down on the edge of a pouch cell, creating a permanent, airtight seal. Finally, we reach sealing. The cell is hermetically closed via high-precision crimping or laser welding. This seal is absolute. It must prevent any moisture from entering, which would cause a catastrophic chemical reaction, and ensure no electrolyte can ever leak out. The cell is now physically complete, but it is not yet a battery. It is a dead vessel, waiting for its first spark of life. Stage 3. Cell finishing, the awakening. Visual. The title Stage 3, cell finishing and activation, appears over a sprawling grid of thousands of glowing LED indicators. We see massive, floor-to-ceiling racks where thousands of individual cells are plugged into automated charging docks. The atmosphere is quieter here, filled with the low hum of cooling fans and the steady click of electrical relays. We have reached the final and most critical phase, cell finishing. Until this moment, the battery is merely an assembly of chemicals and metal. It has no electrical life. In this stage, we carefully wake the cell, breathe energy into it for the first time, and subject it to a rigorous gauntlet of tests to ensure it is worthy of the road. Formation. The first breath, the process begins with formation. This is the cell's first ever charge and discharge cycle, performed at an incredibly slow and meticulously controlled rate. This isn't just about adding power, it's about chemistry. During formation, a vital protective layer called the solid electrolyte interphase, SEI, grows on the anode. This layer is the cell's immune system. It stabilizes the chemistry, ensures safety, and determines how many thousands of cycles the battery will last. Aging and degassing. The stabilizing period. This is a time-lapse shot of a warehouse-sized aging room where cells sit in temperature-controlled racks. We see a robotic arm occasionally pull a cell to check its physical dimensions. Next is aging and degassing. The cells are stored for several days, sometimes weeks, in a controlled environment. We monitor them for any self-discharge, a tiny drop in voltage that could signal a microscopic internal defect. During this time, any gases naturally produced during the formation process are vacuumed out through a temporary opening, and the cell is permanently, hermetically resealed. Only the most stable cells move forward. Finally, we arrive at grading and sorting. Every single cell is tested for its exact capacity, internal resistance, and thermal signature. In 2026, we don't just look for good or bad. We group cells into families with identical performance profiles. This binning process is essential. When these cells are eventually combined into a battery pack for a vehicle, they must work in perfect harmony. A single outlier could limit the performance of an entire car. Conclusion: from a liquid slurry to a high-precision energy powerhouse, the journey is complete. This is the alchemy of 2026, where engineering, chemistry, and extreme automation converge to power our homes, our cities, and our future. The cell is ready. The revolution is charged. What began as raw mineral powders and rolls of metal foil has been transformed. Through the precision of the slurry mix, the architectural stacking of the assembly line, and the first electrochemical breath of formation, we have created more than just a component. We have created the heartbeat of the modern world. In 2026, the quality of this manufacturing process dictates the reach of our ambitions. A more consistent coating means a longer-range vehicle, a more stable SEI layer means a battery that lasts decades, and a more efficient assembly line means clean energy that is accessible to everyone. As these cells leave the factory floor, they carry with them the labor of thousands of engineers and the precision of the world's most advanced AI. They are ready to power our homes, our transport, and our transition to a sustainable planet. The cell is finished. The revolution is charged. The future is in motion. Ever wonder what powers your phone, your laptop, or even your electric car? It all starts with a tiny, powerful component, the battery cell. Let's take a quick peek inside the world of battery production. It's like a high-tech kitchen where incredible precision is key. First, we have the electrodes, a positive cathode and a negative anode. These are coated with special chemical slurries in ultra-thin, perfectly even layers. Think of it like spreading butter on bread, but on a massive, super-fast industrial scale. Next, these coated sheets are precisely cut, stacked, or wound together with a separator in between to prevent short circuits. Then, the entire assembly is placed into a can, filled with an electrolyte liquid that allows ions to flow, and sealed tight. It's a fascinating blend of chemistry and engineering that's powering our future. Want to see more behind-the-scenes tech? Hit that subscribe button and stay charged.